This is problem 11.3. We've got a cantilever retaining wall, sand backfill, the water tables behind it. I never tell you how tough this thing is to build. Typically, you have to build these things in the dry or de-water the area with wells and pumps and stuff like that. Sometimes, because the water table fluctuates, it can become saturated. So that's even though the water wasn't there when you built the thing. Like in Florida, especially where you have sands and heavy rains, the water table can rise pretty quickly. So they made the problem simpler by assuming that the soil above the groundwater table is saturated. So that could happen from a heavy rain, and as the water percolates down through the sand, it fills up the void spaces, so it increases the height of the soil, height of the saturation zone. So regardless, here's the problem. So they give us the void ratio, the coefficient of friction, the specific gravity of the soil solids, and they want you to determine the pressure distribution with depth, the total pressure, and the point of application. So we need to use some soil mechanics equation to come up with the saturated unit weight. Void ratio is 0.56. We use equation 317A on page 25 that relates the saturated unit weight to the void ratio and the specific gravity. We end up at 128.4. So here's the problem again. I've drawn a couple of little pressure diagrams. Remember, we want to do the surcharge, the soil, and the water. So I've assumed that the free water is actually at the groundwater table. So the surcharge, because it's a unbounded load in the half space, Q is 500. The lateral pressure would be equal to Ka times Q, which is 118.9. That's a rectangular pressure distribution. So the total surcharge is just the base times the height. So that gives us a total of 2379 pounds force per foot of wall coming out in the screen. Surcharge of the soil is, I need to use the effective unit weight, so that's gamma sat minus the unit weight of water. I need to use find the area of the maximum pressure, so that's Ka gamma prime times H. So the total pressure is the area of the triangle, 1/2 base times height. So that gives me the total pressure on the soil is 3140 pounds of force per foot of wall. Figuring out the pressure diagram for the water, it's just the unit weight of the water times the height, which gives me 936 psf. The total pressure is the area of the pressure diagram, which is 1/2 the base times the height. So the total pressure is 7,020 pounds force per foot. So when I add those three quantities up, I get 1254.0 pounds force per foot, or 12.5 kips per foot. So now I need to figure the moment arms about the toe for each of those three pressure diagrams. The rectangle is the centroids at half the height, and for the triangular ones, they are at 1/3 up from the base. And to figure the point of application, just sum the moments about the toe, and since I know everything except Z, I can solve that equation for Z, and that gives me the moment arms times the area of the pressure diagram plus the moment arm times the pressure diagram. Sum all that up, and that gives me 6.37 feet.